So the purpose of this lab was to utilize various physical principles of electricity in order to predict and explain the behavior of basic circuits with resistors in parallel and in series, and furthermore to use ammeters to measure electric current and voltmeters to measure potential difference. Some of the fundamental principles explored throughout this lab were Ohm's law, equating voltage, current, and resistance, Kirchhoff's law for explaining how the current into the node equals the current out of the node when there's one entrance and one exit, and how the net change in voltage in a closed loop will be zero. And finally, we're going to explore capacitance and the change in charge over time. Some of the brief final results will that the current will remain the same regardless of our direction. The resistor circuit current is 0.024 amps, and our RC expected was 6 seconds versus our actual of about 10 seconds. So the initial conditions for our series circuit was the system is our circuit, wires, resistors, ammeter, and voltmeter. Our surroundings was everything else, the earth, the table, and the procedure involved creating a circuit with two 1.5 volt batteries in series and two resistors. The resistance for each resistor is outlined in the image to the right, and with those resistances you need to predict and measure current. And this is following the assumptions that there's constant resistance and constant voltage so that we can apply Ohm's law, and the circuit is in a series and it's closed so we can apply Kirchhoff's rule for a closed loop. So the measured current I found was 19.8 milliamps or 0.0198 amps, and calculating the current using Ohm's law, I found 0.0204 amps throughout the circuit, and these are very similar, so we can say they're equal. Finally, some observations where if we reverse direction of the current, then it's going to be just the negative 0.0204 of our current direction, so same magnitude, different sign. And the voltmeter has a higher resistance than our ammeter, so it experiences a reading of 3 volts. All of our charge is dropped at that location, and the ammeter has low resistance, so it takes negligible amounts of current. So the calculations and observations you can see to our right from points C to D and E to F is the only times we're going to have our negative change in potential differences, and this is across our resistors. And calculating the resistance at those points, you can see R of 47 was 46 ohms, R of 100 was 101 ohms, the R of our wire and our ammeter are going to be 0 according to Kirchhoff's rule, and this satisfied the law as the net change in voltage will equal 0. And finally, the current into the node will equal the current out of the node, and we know the current's going to be constant at about 0.204 amps because of the junction rule. So for our parallel circuit, this is when we place our ammeter in parallel with our 100 ohm resistor. I found that it actually adds about a current of 0.054 amps. And you can see in the potential difference graph to our right that by the time the circuit reaches the ammeter, the potential difference is almost 0, and that goes along with our observations. So for the RC circuit, our system was going to be our 10 ohm bulb, the 20 ohm bulb, the 9 volt battery, and the 200 mF capacitor. Our surroundings are again the table, earth, etc. Our initial conditions are that our capacitor has 0 charge, and my observations were that the light started out bright and then it dimmed out as the capacitor charged up. And then finally, when connecting only the light and the capacitor, the light again started out bright and it dimmed out as the capacitor discharged. And you can see my observations for the 10 ohm light bulb, it was about 10.27 seconds to charge the capacitor and 7.7 to discharge. And for the 20 ohm, it was 43 seconds and 44 seconds respectively. And these are different from our calculated values due to human error, issues with the battery, voltage, and maybe the capacitor wasn't exactly as the resistance it was outlined to be. So what if we were doing this lab in real life and used an actual ammeter instead of an ideal ammeter? So the virtual ammeter has an assumed 0 resistance, which allows perfect application of Kirchhoff's rules, while the real ammeter has a slight resistance value, and as a result it had a slight non-negative amount of current, and this could result in a non-net 0 total change in the current throughout the circuit. I just assumed it would be 0 due to the fact that it was so low and that we were trying to show application of Kirchhoff's rules. So what if we were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? As you can be seen in my observed charging times, in real life the amount of time to charge and discharge the capacitor will be longer than our predicted values, and this is because in simulation the resistance of the battery and capacity is assumed to be a perfect 0. However, in real life both of these devices have a small non-zero resistance, so the actual amount of time to charge and discharge the capacitor will always be longer than our simulated time. So some points of error were that the resistance may not have been exact on each resistors, and the batteries might not have had a full 3-volt charge due to other classes using it previously, and the recordings on the ammeter and multimeters might have been off a little, and finally timing the capacitance charge and discharge may not have been exact due to human error between stopping and starting the time. And in our experiment, we assumed that the wire potential voltage differences are 0, which may not be the case in real life. We found when we measured them, they had a very slight amount of charge, and the charge times were not exactly the same, so this shows that the resistance on the light bulbs may not have been exactly as specified. Thank you.